Hello and welcome to this film, which is the second of the higher level atomic structure films. It's all about first ionisation energies. In the previous film we looked at successive ionisation energies, and I suppose it's quite easy to get confused between the two things, so we'll need to be careful to just draw a distinction between what the two different types of ionisation energies are. But hopefully by the end of this film you'll know that the amount of energy that we need to put in to remove an electron from an atom is somehow related to the stability of an atom's electron configuration. And we'll have a close look at some first ionisation energy graphs to see how we can get an even better understanding of how electrons are arranged in atoms by looking at how much energy it takes to remove electrons. Okay, so here is a graph that shows the first ionisation energies of the first 20 elements. Now, say these things can be a bit confusing. You might look at this and think, well, it's quite similar to the graph of potassium's successive ionisation energies that we looked at in the last film. But notice that this particular graph looks at the ionisation energies of 20 different elements. Okay, and it's not about taking one electron away and then another and then another and then another. This is looking at how the amount of energy required to remove that first electron from an atom changes as we go through the first 20 elements in the periodic table. You should know the definition for first ionisation energy, that was covered in the last film, but let's have a look at the most obvious patterns that we see here and try and relate them to what we already know in very basic terms about stability of atoms. Now, as I say, we're just looking at the most obvious things here, like where the massive peaks are. Okay, so there's a big peak at helium, neon and argon, and if you check your periodic table you'll see that they're the noble gases at the end of the first, second and third periods. And you probably know that noble gases have very stable electron configurations. They've got full outer shells, and atoms become stable by gaining full outer shells. So it might not be surprising to see that the atoms who've got really stable electron configurations are the ones that it's hardest to remove electrons from. Okay, if they've got an arrangement of electrons that makes them very stable, they're not going to want to lose electrons. Okay. Similarly, we can see that the group 1 elements, lithium, sodium and potassium, so they're the group 1 elements in the second, third and fourth periods, they've got the lowest first ionisation energy because they find it easy to lose their one electron. Okay, they want to lose one electron to become stable, so it's easy to remove their one electron or their first electron. Okay, so the most obvious thing, I suppose, about this graph is it's showing us that the most stable elements in terms of their electron configurations have the highest first ionisation energies, and the least stable elements have the lowest. In other words, as the first ionisation energy increases, we expect to be finding more and more stable atoms. Okay, now they're the most obvious patterns, but if you look a bit more carefully at what happens as we go across a period, so for example across the second period here or across the third period here, we are getting this gradual rise that we've been talking about from the least stable element to the most stable element, but there's a couple of dips. And remember, if we're saying that the higher your ionisation energy is, the more stable you are, that suggests that beryllium is somehow more stable than boron, and nitrogen is somehow more stable than oxygen, just like magnesium is somehow more stable than aluminium, and phosphorus somehow more stable than sulfur. So again, if we're looking at this for some kind of evidence as to how the electrons are arranged in atoms, then we can say not only are what we've already seen from the successive ionisation energies that there might be 8 electrons that fit in this shell, there might be things that are becoming full within that shell that are giving us more stability. So for example, beryllium might have filled something that means it's more stable than boron. nitrogen might have filled or partially filled something that makes it more stable than oxygen. And we're not going to really go into this now, what these things that we're filling, because they're explained in detail in the next film. But what we're going to say for now is that the dips that we're seeing here, so the dip from beryllium to boron, or the dip from nitrogen to oxygen, is telling us that oxygen has a less stable electron configuration than nitrogen, and boron has a less stable electron configuration than beryllium. And again, if we're looking at this for the first time, so we're trying to make discoveries about an atom, which we're not, someone beat us to that, but if we had been, then we might be thinking that there might be some finer structure within the shells that is getting filled up as we go through the shell. So I just want to summarize the key points for now, because we're going to look at these things in more depth later. Okay, in particular in the periodicity topic, we're going to try and explain more about the reason for the gradual rise in ionization energy. Okay, but for now we're saying that the more stable an atom you are, the more energy should be required to remove an electron from you. Okay, so if one atom has a lower ionization energy than another atom, then the one with the lower ionization energy is probably less stable than the one with the higher ionization energy. And because we're seeing dips as we go across a period, so these little kind of quirks, it suggests that as well as there being shells which hold electrons, there might be some kind of more detailed structure within those shells, which we're actually going to call subshells and orbitals, and we're going to look at those in the next film. Okay, so hopefully at this stage you're thinking that you know something about how the stability of an atom is related to the amount of energy required to remove an electron from it, and you've seen the graphs. Well, hopefully you have seen the graphs if you've watched this film, but you've noticed the similarities and the differences between them and the successive ionization energy graphs, and we've considered how these new graphs are giving us more evidence for the structure of the electron structure within atoms. As usual, if you've got any questions or you'd like to make any comments, please feel free to post a comment on YouTube or to come and find me and ask any questions that you've got.